Welcome, everyone. And today we'll be looking at another very important piece of biological engineering. And I'm sure by now everyone has seen what is projected in this diagram. It's called fish. They are very, very delicious, but also very interesting. It's an aquatic organism, which means it lives underwater. And today I want us to focus on how fish actually conducts respiration, or how respiration takes place in fish, and how they are able to maximize their oxygen intake from the water. And before we even start talking about that, I would love us to understand one thing, and that is that if you look at the amount of oxygen in water and the amount of oxygen that we have in air, the air that we breathe in as land animals, it's very different, such that you're going to find that the oxygen that is present in the water is just a 20th of the oxygen that is present in the air that land animals breathe. So which means for the fish or for aquatic animals, of which today we are mostly focusing on the fish, especially these that are very active, in order for them to be able to get the oxygen that is needed for their metabolic activities in the body, they need to be very efficient in terms of their respiration, their gaseous exchange, their taking up of oxygen from the water, because the oxygen that is in the water is actually very scarce, or it's little when you actually compare it with the normal oxygen that is in the air. So how are fish adapted to this process, or how um, is it possible for or to maximize the intake of oxygen, to maximize the the diffusion of oxygen into the blood? That's where we bring in what we call the counter current flow mechanism. So, ladies and gentlemen, first, if you look at the structure of a fish, I'm sure you can tell from this diagram, which is showing the anatomy of the fish, you're going to notice that the larger part of the body is located that side. And we have this part that is here. And even from primary school, from grade 6, grade 5, grade 1, actually, we already know to say respiration in a fish takes place in an organ that we call a gill. The gills are the ones that are responsible for gaseous exchange in the fish. And that means these guys should be highly adapted to this process of respiration or gaseous exchange in a fish, because they are the ones who are going to be playing a very, very vital role in maximizing the intake of oxygen from the water into the blood or into the bloodstream, and also the carbon dioxide from the bloodstream into the water. So um, let's look at the structure of the gill itself. So if we look at the gill, the structure where gaseous exchange takes place, you're going to notice that the gill is supported by what we call the gill arc, this guy that we have here. And on the gill arc, there is what we call the filaments. So we have these finger-like structures there, a pair of finger-like structures that we call the filaments. And the filaments are made up of what we call the primary lamella, no, the primary lamellae. So these lamellae, or the lamellae is the actual structure where the gaseous exchange is going to take place, because uh, they are highly folded. On the primary lamellae, you're going to find that they are the lamellae is going to get highly folded into what we are calling the secondary lamellae. This one that we have here is going to get highly folded into what we call the secondary lamellae. And the secondary lamellae is having a large number of capillaries, as we can see here. We are having a large number of capillaries, blood vessels, capillaries. And the if we look at the epithelial lining of the secondary lamellae, you're going to find that it's just one or two cells thick. And this thickness is going to maximize the diffusion of gases into and outside of the bloodstream. because gaseous exchange is going to be taking place through diffusion, or gases are going to be moving in and outside the bloodstream using diffusion. And how is the secondary lamellae adapted to that? Is by being extremely thin. It is just about one or two layers of cells thick. The epithelial lining is very thin, such that it is adaptive to maximum diffusion of gases into and outside, or into and out of the bloodstream. So you are going to have your water entering the fish through the mouth. The fish will be taking in water through the mouth, and the water will be passing through the gills. And uh, it is going to be flowing systematically in that manner to the lamellae, where you have your foldings in the secondary lamellae. The foldings are just there to maximize the surface area for gaseous exchange until they reach the the capillaries, where the actual exchange of gases will actually be taking place. So this exchange is following what we are calling the counter current um, mechanism. So we need to understand how this mechanism now is going to be helping to, or how this mechanism will help the fish actually maximize the intake of oxygen. Because from the 20th, or the 20th of oxygen that is present in the water, you're going to find that the fish is going to be able to take up 8 to 90% of that oxygen into the bloodstream, thereby maximizing this process actually very efficient. And how is that happening? Let's just zoom in on the gill, or the lamella itself, the secondary lamellae. Okay, so in this picture, you can now see the actual mechanism of flow, the mechanism that we are calling the mechanism that we are calling the counter current flow mechanism. So in this mechanism, ladies and gentlemen, you're going to notice that the blood flows in the opposite direction to the water that is passing over the lamellae. The water is moving from this direction over the lamellae into, or to the left, whilst the blood is moving from the right to the left in the opposite direction. This is what we're calling the counter current flow. This counter current flow, you're going to notice that this blood that is entering the lamellae from the left, which is very deoxygenated, is going to be meeting the water that is about to exit the gill. This water that is about to exit the gill actually has a very low, but still present oxygen concentration. You can see to say there is a low concentration of oxygen. The partial pressure of oxygen is just about 15%, but it's still present. Whilst if you look at the presence or the partial pressure of oxygen that is in the deoxygenated blood, it is very low, just about 5%. This water is having a high concentration of oxygen than the blood that is meeting just before it exits the fish. So there is a concentration gradient that is created here, because gases are always diffusing from a higher concentration to a lower concentration. And since it's gases here, we're going to say they are always diffusing from a higher partial pressure to a lower partial pressure. So you can see to say this blood is highly deoxygenated, and it is meeting the water that is about to exit the gills, which is low in oxygen. But the concentration of oxygen in the water that is about to exit the gill is still slightly higher than the deoxygenated blood that is meeting, thereby having a concentration gradient. And since there's still a gradient there, oxygen will be diffusing from a higher partial pressure to a lower partial pressure, meaning oxygen is diffusing from the water into the blood, despite the lower concentration of oxygen in the water that is there. As the blood is flowing along the lamellae, you can see what is happening even up to the center there, as the blood is flowing along the lamellae. It is going to be gaining oxygen, but it is going to be constantly meeting water that is progressively richer in oxygen concentration, because you can see here the partial pressure of oxygen in the blood has significantly increased to 30%, but it is still meeting water that is progressively increasing in the partial pressure of oxygen. As you can tell here, there's still a 40% partial pressure in oxygen, still creating a concentration gradient. There's still a difference, a slight difference in the partial pressures of oxygen between the water and the blood. Hence, oxygen will still be diffusing from the water into the blood. And the same, ladies and gentlemen, happens at the beginning there, or should I say at the end, because it is the beginning here and the end there. At that end, ladies and gentlemen, I'm sure you can tell to say the the highly oxygenated blood now that is about to leave on the left is still meeting what? Is still meeting the fresh incoming water from the mouth of the fish. The highly oxygen-rich blood that is about to exit the lamellae or the gill is still meeting the incoming fresh water from the mouth, and this water is still having a high amount of oxygen as compared to the blood. The oxygen in the blood is about 90%, whilst the oxygen in the water is about 100% because it is fresh. It hasn't been reduced from anywhere. So there's still a concentration gradient that has been maintained there, which means oxygen is still going to be flowing to be diffusing from the water into the the bloodstream. Hence, the mechanism that we are calling the countercurrent mechanism, ladies and gentlemen, is maintaining a concentration gradient. From the beginning, this point, up to the end, that point, we're still having a concentration gradient, allowing the oxygen to be continuously flowing. Just as the blood meets the water that is about to leave the operculum of the fish, or to leave the fish to the operculum, to the point where the water is entering the lamellae or the gills of the fish, there's still a concentration gradient that is maintained along this path. Hence, oxygen will be continuously diffusing from the water into the bloodstream, thereby maximizing the intake of oxygen from the water. And this, ladies and gentlemen, is going to lead up to the intake of about 80 to 90% of the oxygen that is present in the water. Hence, we say the countercurrent flow mechanism will maximize the intake of oxygen from the water into the bloodstream of the fish. So if you try and compare this, ladies and gentlemen, to the parallel flow mechanism or the co-current mechanism, you're going to notice, okay, so this was just another simplified diagram, but if you compare this to the co-current mechanism, you're going to notice that the concentration gradient is not maintained. It reaches a point where if you're having blood and water flowing in the same direction, it is going to reach a certain point where the concentration of oxygen is the same in both the the water and the blood, such that there will be no net movement or net movement of oxygen molecules because the concentration is the same. Hence, there will be no net flow of molecules from either the water to the the bloodstream or the bloodstream to the water. Hence, this one is the one which maximizes the uptake of oxygen from the water to or into the blood. And just like that, ladies and gentlemen, we have explained how the countercurrent flow mechanism actually maximizes oxygen uptake from the water into the blood. So thank you very much for watching this video. Make sure you subscribe, you share, and also register with our tuition center using the procedure that I've indicated in the description of the video and also the description of my YouTube channel. Until next time, stay blessed.